On December 19, 2025, an object older than the Sun will slide past Earth at a distance of about 270 million kilometers, roughly 170 million miles, almost twice as far as the Sun and more than 700 times the distance to the Moon. It has a name that sounds almost mechanical: 3 Atlas, the third confirmed interstellar visitor in human history. Right now, as you listen, telescopes across the planet are racing a clock. Hubble and ESA's JUICE probe have already captured detailed images. ALMA has measured strange, rich plumes of methanol and hydrogen cyanide, chemicals we usually talk about in the context of life's early chemistry. NASA's Planetary Defense Network is treating December 19th as a global stress test, not because 3I Atlas is dangerous, but because it is unknown. The anomalies keep stacking. The comet's brightness pulses on a 16.16-hour heartbeat that no one can fully explain. Its tails don't behave. A sharp, sun-facing anti-tail cuts against textbook comet physics, as if dust and gas are obeying some hidden geometry instead of gravity and sunlight alone. For a few hours on December 19th, Earth, 3 Atlas, and a ring of space telescopes will fall into a fragile alignment, the final observation window before this object fades into deep interstellar darkness, beyond any instrument we can build in our lifetimes. This episode is the full story of that alignment window. The discovery, the anomalies, the quiet arguments behind closed doors, and what this object might be telling us about life, technology, and the way the universe moves things between stars. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. This is 3 Atlas, the full story behind its December 19 alignment window. This is not science fiction. This is December 2025. Chapter 1. July 1st, the telescope that caught an interstellar stranger. The Asteroid Terrestrial Impact Last Alert System. Atlas for short is not designed for glory. It is designed for survival. 4 robotic telescopes, scattered across 2 continents, scan the sky every night, sweeping through sectors in a relentless grid. Their mission is simple and terrifying: find asteroids before they find us. Every faint point of light gets logged, measured, compared against catalogs. If something moves wrong, if something accelerates where it shouldn't, alarms go off. On July 1st, 2025, at 3:14 Universal Time, the Atlas station in New Mexico flagged an object. The detection was unremarkable at first. A 16th magnitude blur, roughly 100,000 times fainter than what the human eye can see, drifting through the constellation Lyra. The automated pipeline marked it, cross-referenced it against known asteroids and comets, found no match, and forwarded it to the Minor Planet Center in Cambridge, Massachusetts. 6 hours later, Atlas Chile confirmed it. Same object, slightly different angle, moving fast. By the afternoon of July 2nd, observers in Europe and Japan had added their own measurements. The orbit solution came back within 48 hours, and that's when everything changed. The object wasn't orbiting the Sun. It was passing through. Eccentricity greater than 1. Hyperbolic trajectory. Incoming velocity that couldn't be explained by solar gravity alone. The numbers were clean, the error bars tight. There was no ambiguity in the math. This thing came from somewhere else. By July 4th, it had a provisional designation, C-2025, none. By July 7th, after enough observatories had contributed data to lock down the orbit with confidence, it received its formal name, 3 Atlas. The third interstellar object ever confirmed by human instruments. The first was Oumuamua in 2017, a tumbling, elongated enigma that refused to fit into any comfortable category. Too red to be a comet, too fast to explain without gassing alone, and gone before anyone could get a good look. The second was Toei Borisov in 2019, a textbook comet, familiar and almost boring in its normalcy. It reassured the astronomical community that interstellar objects could be mundane, that Oumuamua might have been the exception, not the rule. Now there was 3 Atlas, and it didn't feel mundane at all. The discovery process unfolded in layers. On the front end, The planetary defense software treated 3I Atlas like any other near-Earth object. Risk assessments ran automatically. Impact probabilities were calculated, recalculated, refined. Within 72 hours, the conclusion was clear: zero threat. The comet would pass Earth at a distance of 1.8 astronomical units, about 170 million miles, on December 19. Not even close, by cosmic standards. But on the back end, in email threads and Slack channels and hastily scheduled Zoom calls, a different conversation was starting. Some voices insisted this was routine. Interstellar comets were predicted by theory. Models of stellar nurseries and gravitational scattering said billions of these objects should be drifting through the galaxy at any given time. We'd only seen 3 because our telescopes were finally good enough to catch them. Finding more wasn't a surprise. It was statistics. Others weren't so sure. Dr. Elena Vargas, a comet dynamicist at the European Space Agency, sent a memo to her team on July 3. The subject line read, "Priority flag, hyperbolic visitor." In the memo, she outlined 3 reasons why 3A Atlas deserved more than routine follow-up. First, its orbit brought it unusually close to the inner solar system. Oumuamua had skirted past the Sun at 0.250, closer than Mercury. Borisov stayed farther out, around 2.0 at perihelion, roughly Mars distance. 3. Atlas was threading the middle. 0.650, just inside Venus's orbit, close enough to heat up, outgas, and potentially reveal its internal composition in ways the others hadn't. Second, its discovery came at a moment when the international community was finally coordinating around interstellar object response. After Oumuamua's flyby, dozens of mission concepts had been drafted: fast response probes, gravity tractors, rendezvous orbiters, but none had been funded. After Borisov, the conversation shifted to preparation: better detection networks, faster alert systems, international agreements on who gets to make first contact. 3 Atlas was arriving just as those plans were moving from PowerPoint slides to actual hardware proposals. Third, and most quietly, Vargas noted that the object's brightness behavior was non-standard. Early photometry from Atlas and follow-up observations suggested the comet was brighter than expected for its size and distance, and that brightness was fluctuating in ways that didn't match the smooth outgassing curves of typical comets. She didn't use the word anomaly in the memo, but she didn't have to. By July 5, NASA's Planetary Defense Coordination Office had added 3 Atlas to its tracking list, not as a threat, but as a high-priority science target. The language was careful. The object was safe. But it was also important. On July 6, Dr. Avi Loeb, Harvard astrophysicist, director of the Galileo Project, and the most prominent voice arguing that Oumuamua might have been artificial, published an op-ed in Scientific American. The headline: "We should treat every interstellar visitor as a potential messenger." In it, he argued that the probability of any single interstellar object being a technosignature was low, but the cost of ignoring one was catastrophically high. He compared it to the search for extraterrestrial intelligence. You don't expect every star to host a transmitting civilization, but you point your radio telescopes at them anyway, because the payoff of a single detection justifies the investment. 3 Atlas, he wrote, was already showing signs that demanded attention. Its trajectory, its brightness, its timing. He stopped short of claiming it was artificial, but he didn't rule it out either. The essay was shared 40,000 times in the first 12 hours. Inside NASA, the reaction was mixed. Some scientists appreciated the publicity. It helped justify the telescope time they were requesting. Others worried that premature speculation would poison the well, turning serious research into a media circus. But everyone agreed on one thing: this object mattered. On the evening of July 7th, as the formal designation 3 Atlas was entered into the International Astronomical Union's database, Dr. Michael Torres sat alone in his office at the Jet Propulsion Laboratory in Pasadena. He had spent the day running trajectory simulations, refining the orbit, modeling where 3I Atlas would be in the coming months. December 19th kept showing up as a critical date. That was the day Earth would be best positioned to observe the comet as it exited the inner solar system, moving outbound at roughly 60,000 miles per hour. After that, it would fade. By February 2026, even Hubble wouldn't be able to resolve it. By summer, it would be gone, a 16th magnitude ghost retreating into the interstellar void. Torres saved the simulation and stared at the screen. 6 months. That's all they had. He thought about Oumuamua, how it had appeared and vanished before anyone realized what they were looking at. He thought about Borisov, how much they'd learned because they'd had time to prepare. He opened a new email and started typing. The subject line, December 19th alignment window, request for Hubble time. Out here, nothing is random. Chapter 2, July 7th, when Interstellar Comet became official. There's a specific moment when something stops being a curiosity and becomes a fact. For 3 Atlas, that moment came on July 7th, 2025, at 1842 UTC, when the Minor Planets Center issued circular Nobadoriz 108,442, formally designating the object as C2025 non-Atlas, and confirming its interstellar origin with an orbital eccentricity of 1.034 to 0.00. Eccentricity is a measure of how stretched an orbit is. A perfect circle has an eccentricity of 0. Earth's orbit, which is nearly circular, has an eccentricity of 0.017. Most comets in our solar system have eccentricities between 0.9 and 0.99, meaning they follow long, elliptical paths but remain gravitationally bound to the Sun. Anything above 1 is hyperbolic. It means the object is moving too fast to be captured. It's passing through, not staying. 3I Atlas's eccentricity of 1.034 meant it was moving at 34 kilometers per second relative to the Sun's rest frame, faster than solar gravity could hold. Trace it backward, and the trajectory didn't loop. It stretched out in a straight line, pointing toward a region of space near the constellation Cassiopeia. That was where it came from. And when it left the solar system, it would head somewhere else entirely. The announcement landed in inboxes around the world within minutes. Observatories scrambled to book telescope time. Data pipelines adjusted their priorities. Amateur astronomers checked their sky charts, calculating whether 3I Atlas would be visible from their backyards in the coming months. The name itself carried weight. The 3I prefix marked it as the third interstellar object, joining Oumuamua and 2I Borisov in a category that had not existed a decade earlier. Dr. Karen Meech, a planetary scientist at the University of Hawaii who had led much of the observational campaign for 2I Borisov, sent a message to her team that evening. We have 6 months to learn everything we can. Don't waste a single night. By July 8th, comparison studies were already circulating on Arxiv, the open-access physics preprint server. Researchers lined up 3 Atlas against its 2 predecessors, cataloging similarities and differences. Oumuamua had been small, dark, and inert. No visible coma, no tail, no outgassing detected. Its dimensions were estimated at roughly 400 meters by 40 meters, an elongated shape that made some researchers think of a shard, others of a light sail. Its surface was red, covered in organic tholins, radiation-baked carbon compounds common in the outer solar system. But it had accelerated as it left, a tiny, unexplained push that didn't match standard comet models. 2I Borisov had been the opposite. A classic comet, complete with a bright coma and twin tails of gas and dust. Spectroscopy revealed water vapor, carbon monoxide, and cyanide, standard comet chemistry, indistinguishable from solar system natives. Its nucleus was about 1 kilometer across, and it behaved exactly as textbooks said it should. Reassuring. Almost boring. 3A Atlas fell somewhere in between. Initial size estimates based on brightness and assumptions about surface reflectivity suggested a nucleus roughly 2 to 4 kilometers in diameter. Larger than Borisov, but not dramatically so. Its color was slightly redder than Borisov, but bluer than Oumuamua, suggesting a surface composition somewhere in the middle. But then, there was the outgassing. Comets are dirty snowballs, mixtures of ice and rock held together by gravity and chemistry. When they approach the Sun, solar heat vaporizes surface ices, releasing gas and dust in plumes that form the coma and tails we associate with comets. The amount of outgassing depends on distance from the Sun and the comet's composition. Closer means hotter. More volatile ices mean more gas. 3 Atlas, in early July, was still 3.50 from the Sun, about halfway between Mars and Jupiter. At that distance, water ice doesn't sublimate much. Carbon dioxide ice can start to release gas, but the activity should be faint. Yet, 3 Atlas was already showing a detectable coma. Dr. Luca Marenzi, an observational astronomer at the Asiago Observatory in Italy, captured some of the first resolved images of the coma on July 9. His images showed a fuzzy asymmetric envelope around the nucleus, roughly 10,000 kilometers across, faint but unmistakable. He ran the numbers. For a coma that size at that distance, 3I Atlas had to be releasing several hundred kilograms of material per second, more than expected, more than Borisov had been doing at the same distance. The data was preliminary. Error bars were large, but it was enough to raise eyebrows. On July 10th, Meek's team at the University of Hawaii secured time on the Gemini North Telescope to obtain spectroscopy, splitting the comet's light into wavelengths to see what molecules were present in the coma. The first spectrum came back on July 12th. Carbon monoxide, strong, kilotramsa, cyanide, detectable, water vapor tash, present, but weaker than expected, and something else. A faint emission line at 352 micrometers, consistent with methanol. Methanol is a simple organic molecule, one of the building blocks for more complex chemistry. It's found in star-forming regions, in interstellar clouds, and in comets. But it's rarely abundant. In most solar system comets, methanol accounts for less than 2% of the total gas output. In 3A Atlas, even in these early observations, it appeared to be closer to 5%. That was unusual. Not impossible. Not unnatural. But unusual. Dr. Clara Nguyen, an astrochemist at MIT, saw the data and immediately thought of the early solar system. Methanol is a marker of cold, distant formation environments. The kind of icy, molecule-rich regions where planets and comets first condense out of protoplanetary disks. If 3I Atlas was unusually rich in methanol, it might mean a comet formed in a region colder and more chemically active than the environments that produced most solar system comets. It might mean it came from a younger star system, or a different kind of star altogether. Nguyen sent an email to Meech. We need ALMA. ALMA, the Atacama Large Millimeter Submillimeter Array, is one of the most powerful radio telescope networks on Earth, designed to detect the faint millimeter wavelength emissions of molecules in space. It can measure not just the presence of chemicals, but their abundances, their temperatures, their motion. If 3I Atlas was carrying a rich chemical cargo, ALMA would see it. But ALMA time is precious, and the comet was still far away. Meech added it to the list of requests. Meanwhile, the debate about what 3 Atlas meant was already heating up. In a blog post on July 13th, Dr. Avi Loeb returned to the subject. He pointed out that 3 interstellar objects in 8 years was statistically surprising. Models based on stellar dynamics and population estimates suggested we should see 1 or 2 per decade, not 3 in less than 1. Either the models were wrong, he argued, or we were living through a statistically unlikely cluster. Or, he added carefully, some of these objects weren't random. He didn't elaborate. He didn't need to. The implication hung in the air. If even one interstellar object was artificial, the detection rate would look different. You'd see more than chance alone would predict. The response from the broader community was swift and skeptical. Dr. Paul Weissman, a veteran comet scientist at the Planetary Science Institute, published a rebuttal on July 15. He argued that detection rates depend heavily on survey capabilities, and that Atlas, Pan-STARRS, and other modern systems had only recently reached the sensitivity needed to catch faint, fast-moving objects. The spike in detections was an artifact of better technology, not a sign of anything unusual. We're finally good enough to see what was always there, he wrote. But he also acknowledged that 3 Atlas deserved scrutiny. This is a comet, he concluded. But it's a comet we've never met before, and that's worth paying attention to. By the end of July, the object had faded slightly as it continued inbound, but the interest had not. Observing proposals piled up at NASA, ESA, and independent observatories. Researchers requested time on Hubble, GWST, ALMA, VLT, Keck, and Gemini. Some wanted to study the comet's chemistry. Others wanted to measure its rotation, map its surface, or model its dust production. Everyone wanted December 19th, because the geometry mattered. On that date, Earth would be positioned such that the comet, the Sun, and a constellation of space-based observatories would align in a way that maximized observational coverage. Hubble and GWST could image it in visible and infrared light. ALMA could measure its molecular emissions. ESA's JUICE probe en route to Jupiter would have a clean sightline from 41 million miles away, offering a second perspective. It was a fleeting alignment, a product of orbital mechanics and timing. After December 19th, the angles would worsen. The comet would fade. The window would close. Dr. Torres at JPL updated his simulation. He added markers for every major telescope and spacecraft, color-coded by wavelength and capability. The alignment window was 18 hours long. That was all. He stared at the screen and thought about Oumuamua again, how it had slipped away before anyone could coordinate a proper campaign. This time, they had warning. This time, they had a plan. But they also had 6 months to wait. 6 months during which the comet would get closer, brighter, stranger. And 6 months for something to go wrong. Out here, nothing is random. Chapter 3, October 3rd, The Mars Flyby and the First Thin Tail. By October, 3E Atlas was no longer a distant smudge. It was moving inbound at 37 kilometers per second, roughly 83,000 miles per hour, on a trajectory that would take it deep into the inner solar system. On October 3rd, it crossed Mars's orbital path at a distance of 1.52 astronomical units from the Sun, about 142 million miles. Mars itself was nowhere near the crossing point. The planet was on the other side of its orbit, more than 200 million miles away. But NASA's Mars Reconnaissance Orbiter, or MRO, happened to be looking in the right direction. MRO is a workhorse. Launched in 2005, it has spent 2 decades mapping Mars, studying its atmosphere, scouting landing sites, and relaying data from surface rovers. Its high-resolution imaging science experiment camera, HiRISE, can resolve features on the Martian surface as small as a kitchen table. Pointing it at a comet 200 million miles away was not standard procedure. But Dr. Sarah Milkovich, a planetary geologist at JPL and part of the HiRISE operations team, saw an opportunity. On September 28th, she submitted a request to retarget the camera during a brief maintenance window when MRO wasn't committed to surface observations. The request was approved. On October 3rd at 1422 UTC, HiRISE captured 3I in Atlas. The image was grainy, a product of distance and the camera's narrow field of view, but it was enough. The comet appeared as an elongated blur, its nucleus unresolved, but its coma clearly visible, a faint, asymmetric halo roughly 15,000 kilometers across. And trailing behind, faint but unmistakable, was a tail. It was thin, wispy, stretching perhaps 50,000 kilometers. In the context of comets, that was underwhelming. Bright comets can have tails tens of millions of kilometers long, visible to the naked eye from Earth. 3 Atlas's tail, by comparison, was modest. But it was there. And that mattered because it was earlier than expected. Dr. Jianyang Li, a planetary scientist at the Planetary Science Institute, who specializes in comet dust dynamics, received the HiRISE data on October 4th. He immediately ran a model to estimate the amount of dust being released. For a tail that size at that distance, the comet had to be producing about 10 to 20 kilograms of dust per second. Not a lot, but more than Borisov had been releasing at the same heliocentric distance. And yet, paradoxically, the gas output was much higher. Spectroscopy from ground-based observatories in late September had shown that 3I was releasing hundreds of kilograms of gas per second, carbon monoxide, cyanide, water vapor, and that persistent methanol signature. The gas-to-dust ratio was off, skewed heavily toward gas. In a typical comet, gas and dust come out together, mixed in a ratio about 1:1 by mass. Some comets are dustier, others gassier, but the variation is usually modest. 3 Atlas was producing roughly 10 times more gas than dust. Lee sent a note to his colleague, Dr. Matthew Knight, at the U.S. Naval Observatory. "This thing is more like a steam vent than a snowball." Knight ran his own models and came to a similar conclusion. For the dust-to-gas ratio to be that low, the comet's surface had to be unusually volatile-rich, with large reservoirs of ices that sublimate easily, and relatively little rocky or dusty material. Or, he noted in a follow-up email, the dust was being held back somehow, trapped beneath the surface, released in bursts rather than a steady flow, or perhaps interacting with the gas in ways that standard models didn't account for. He flagged it as anomaly number 2 after the unusually high methanol abundance. The list was growing. Meanwhile, ground-based observers were struggling. As 3I Atlas moved closer to the sun through October, it was also moving closer to the sun in the sky, edging toward the solar glare as viewed from Earth. By mid-October, it was less than 40 degrees from the sun, which meant it could only be observed for a brief window after sunset or before sunrise, low on the horizon where atmospheric distortion was worst. Dr. Helena Rodrigues, an astronomer at the European Southern Observatory in Chile, had scheduled observation time on the Very Large Telescope for October 10. But when the night came, the comet was too low. Atmospheric turbulence smeared the image. She captured a few frames, but the data was marginal, barely usable. She tried again on October 14. Worse. By October 20th, 3A Atlas was too close to the sun to observe from the ground at all. It was entering conjunction. The weeks leading up to perihelion, the comet's closest approach to the sun, would be a blackout period. Most Earth-based telescopes would lose it entirely, unable to point that close to the solar disk without risking damage to their instruments. There were exceptions. Solar observatories, designed to stare at the sun, could catch the comet as it passed through their field of view. NASA's Solar and Heliospheric Observatory, SOHO, and ESA's Solar Orbiter both had coronagraphs, instruments that block the sun's bright disk to reveal the faint corona and any objects passing nearby. Dr. Carl Badams, a solar scientist at the Naval Research Laboratory who runs the Sun-Grazing Comets project, flagged 3I Atlas in the SOHO observation schedule. If the comet passed through SOHO's field of view near perihelion, they'd get a glimpse. But it would be brief, and the data would be limited. For most of the astronomical community, October 20th through November 15th was a waiting game. Dr. Meach, coordinating the International Observation Campaign from Hawaii, sent a note to her network, "Stay ready. It'll come out the other side. And when it does, we need to be on it immediately." Behind the scenes, however, a quieter concern was growing. The blackout period meant no direct imaging, no spectroscopy, no way to monitor how the comet was behaving as it heated up near perihelion. If 3I Atlas did something unexpected during that time, if it brightened suddenly, if it fragmented, if it released a burst of gas or dust, they wouldn't see it until it was over. Dr. Torres, at JPL, updated his tracking model daily, using pre-conjunction data to predict where the comet would be when it emerged. His simulations showed a healthy margin of error. The orbit was well constrained, but comet behavior near perihelion could introduce non-gravitational accelerations, tiny pushes from outgassing jets that altered the trajectory in unpredictable ways. Oumuamua had experienced non-gravitational acceleration, so had many solar system comets. If 3I Atlas did the same, the December 19th alignment window might shift by hours or even days. He flagged it in his report to NASA's Planetary Defense Office. Recommend contingency plans for schedule adjustment post-perihelion. The report was filed, read, and noted. On October 25th, deep in the conjunction blackout, something happened that no one saw in real time. Soho's LASCO T3 coronagraph, which images the sun's outer corona out to about 30 solar radii, captured a faint streak in its field of view. The object was too far from the sun to be a sun-grazing comet, but too faint to resolve clearly. The data sat in the Soho archive, waiting to be processed. It would be another 2 weeks before anyone noticed. But when they did, they'd realize that 3E Atlas had done something strange. Something that comets weren't supposed to do. Out here, nothing is random. Chapter 4, October 29th, Perihelion and the physics that didn't add up. Perihelion is the moment of truth for a comet. It's the closest point to the sun, the moment of maximum heating, when solar radiation hammers the nucleus and drives sublimation at its most intense. Some comets survive perihelion and emerge brighter, their tails streaming behind them in triumph. Others fragment, torn apart by thermal stress or tidal forces, scattering into rubble. For 3I Atlas, perihelion came on October 29, 2025, at 11:34 UTC. Distance from the sun: 0.647 astronomical units, about 60 million miles, just inside the orbit of Venus. At that distance, sunlight is nearly 3 times as intense as it is at Earth. Surface temperatures on the comet's sunlit side would spike to around 200 degrees Celsius, hot enough to vaporize water ice aggressively, along with carbon dioxide, carbon monoxide, methanol, and more volatile compounds. The models predicted a dramatic increase in activity, but no one could see it. 3I Atlas was lost in the glare, hidden behind the sun as viewed from Earth, observable only by a handful of solar-pointing spacecraft that happened to catch it in passing. Soho's LASCO C3 coronagraph recorded the comet as a faint streak on October 27th, 28th, and 29th. The images were low resolution, heavily processed to subtract the sun's overwhelming brightness, but they showed something. Dr. Badams, reviewing the LASCO data on November 1st, noticed it immediately. The comet's tail wasn't where it should be. In a normal comet, the tail points away from the sun, pushed by solar radiation pressure and the solar wind. It's one of the most reliable rules in cometary physics. The tail follows the anti-solar direction, give or take a few degrees depending on the comet's motion and the structure of the solar wind. But in the LASCO images, 3E Atlas's tail was offset. Not dramatically, maybe 10 or 15 degrees, but enough to be noticeable. The tail wasn't pointing directly away from the sun. It was tilted, skewed, as if the dust and gas were responding to something other than radiation pressure alone. Badams ran the images through an enhancement pipeline, sharpening the contrast and filtering out noise. The tail's offset became clearer. He sent the images to Dr. Geraint Jones, a space plasma physicist at University College London, who specializes in comet-solar wind interactions. Jones looked at the data and frowned. Tail anomalies weren't unheard of. Comets could develop multiple tails, one of gas, one of dust, and those tails could point in slightly different directions depending on particle size and charge. The solar wind itself could be structured, with fast and slow streams that bent and twisted plasma tails in complex ways. But this looked different. The offset was consistent across multiple frames, and it didn't match the expected geometry for a standard dust tail or a standard ion tail. "It's like the tail is being pulled," Jones said in a video call with Badams on November 3rd. But pulled by what? One possibility was magnetic fields. If the comet was releasing a lot of ionized gas, charged molecules, and if the local interplanetary magnetic field had an unusual structure near perihelion, the plasma could be dragged along field lines rather than flowing straight back with the solar wind. It was a reach, but it was plausible. Another possibility was that the tail was actually 2 tails, overlapping in projection, creating an illusion of offset. Or, Jones admitted, the data was just too low resolution to trust. "We need better images," he said. But by then, 3 Atlas was already past perihelion, moving outbound, still hidden in the sun's glare. They'd have to wait for it to emerge. Meanwhile, another anomaly surfaced. Dr. Torres, at JPL, had been running daily trajectory updates using pre-perihelion observations. His model predicted where the comet should appear when it came out of conjunction in mid-November. But on November 2nd, he received a preliminary orbital update from ESA's Near-Earth Object Coordination Center, based on the LASCO images. The comet was slightly off course. Not by much, only about 0.3 degrees in sky position, but enough to be significant. The difference corresponded to a change in velocity of roughly 3 meters per second. That was a non-gravitational acceleration. Torres wasn't surprised. Comets experience non-gravitational forces all the time, mostly from outgassing. When jets of gas erupt from the sunlit side of the nucleus, they act like tiny rocket engines, giving the comet a push. The effect is usually small, but measurable. What surprised him was the direction. Most comet non-gravitational accelerations point roughly away from the sun, because that's where the outgassing is strongest. But 3I Atlas's acceleration, based on the orbital shift, seemed to be tilted, not purely radial, not purely tangential, but somewhere in between. He ran a simulation to see what kind of outgassing pattern could produce that acceleration. The answer: an asymmetric jet, probably on the night side of the nucleus, releasing gas in a direction that didn't align with the comet's rotation axis or the sun's direction. Possible. Even likely. But also, Torres noted, exactly what Oumuamua did. Oumuamua's non-gravitational acceleration had been one of the most controversial aspects of its flyby. The object had sped up as it left the inner solar system, a small but unmistakable push that couldn't be explained by solar gravity alone. Some researchers attributed it to outgassing, water vapor or carbon monoxide sublimating from the surface. Others pointed out that no cometary activity had been detected, no coma, no tail. If Oumuamua was outgassing, it was doing so invisibly. That opened the door to alternative explanations. Maybe it wasn't outgassing. Maybe it was something else. A light sail, some suggested. A thin, reflective sheet pushed by sunlight. Or maybe it was a fragment of a larger object, tumbling and venting in ways we couldn't model. The debate had never been resolved. Now, 3I Atlas was showing a similar pattern, non-gravitational acceleration that didn't quite fit standard outgassing models. Torres filed the observation in his report, flagged it for follow-up, and kept running the numbers. On November 7th, as 3I Atlas began to emerge from the far side of the sun, Dr. Rodrigues at ASO secured observation time on the VLT. The comet was now outbound, 0.80 from the sun, moving away at 35 kilometers per second. It was still low in the sky, still difficult to observe, but just barely accessible. On the night of November 8th, Rodrigues pointed the VLT's Force 2 spectrograph at 3I Atlas and captured a 10-minute exposure. The spectrum came back the next morning. Water vapor (muito), strong. Carbon monoxide ((D), very strong. Cyanide, present. Methanol, still elevated around 6% of the total gas production. And one more thing. A faint emission line at 157 nanometers, detectable only because Force 2 happened to catch it in a narrow spectral window. Hydroxyl radical. Hydroxyl is a fragment of water, produced when solar ultraviolet light breaks apart HAO molecules in the coma. It's common in comets, a standard marker of water outgassing. But the intensity was off. Rodrigues ran the numbers. The amount of O suggested the comet was releasing about 500 kilograms of water per second. But the infrared data, which directly measured HEO, suggested only 300 kilograms per second. The ratio was wrong. Either the comet was producing more hydroxyl than the water content could explain, or something was breaking apart water molecules faster than normal. Rodrigues sent the spectrum to Dr. Nguyen at MIT. Nguyen stared at the data for a long time. "This doesn't make sense," she finally said in an email. "Unless there's another source of hydroxyl, something that isn't water." She ran a chemical model, testing different scenarios. One possibility: methanol. If methanol was being photodissociated, broken apart by sunlight, it could produce hydroxyl along with other fragments. But the methanol abundance would have to be even higher than they'd measured. Much higher. Nguyen flagged it as anomaly number 3. The list was growing longer. By mid-November, 3 Atlas was fully emerged from conjunction, bright enough to observe consistently, and the international campaign shifted into high gear. But the October data had left everyone uneasy. The tail offset, the non-gravitational acceleration, the hydroxyl anomaly. Individually, each could be explained. Comets were messy, unpredictable, full of surprises. But collectively, Dr. Meach called a meeting on November 12th, a virtual roundtable with 24 researchers from around the world. The question on the agenda: are we looking at a comet, or are we looking at something else? The room, virtual as it was, split. Half argued this was still a comet, just a weird one. Interstellar objects were expected to be different. They formed in other star systems, under different conditions. Of course, they'd have unusual chemistry, odd rotation, strange tails. That was the whole point. The other half pointed out that weird but natural was starting to feel like a default assumption, a way to avoid harder questions. How many anomalies, one researcher asked, does it take before we stop calling them anomalies? No one had a good answer. The meeting ended inconclusively, with the agreement to continue observations and see what December brought. But privately, several participants started drafting papers exploring alternative hypotheses. Not all of those papers would mention the word artificial, but some would. Out here, nothing is random. Chapter 5, November 30th, Hubble, Juice, and a Sky Full of Instruments. By late November, the clock was ticking loud enough for everyone to hear. 3 Atlas was now 1.1 astronomical units from the Sun, roughly 102 million miles, moving outbound at 33 kilometers per second. It was still bright, still active, releasing gas and dust at a rate that exceeded most predictions. And it was 3 weeks away from the alignment window. On November 30th at 2:17 UTC, the Hubble Space Telescope locked onto 3 Atlas. Hubble is old. Launched in 1990, it has spent 35 years orbiting Earth, staring into the cosmos, capturing images that have redefined how we see the universe. Its mirrors are aging, its instruments have been repaired and replaced multiple times, and its gyroscopes are failing one by one. But it still works. And when you need a sharp, high-resolution image of a faint, distant comet, there's still nothing better. The observation was a multi-band exposure using the Wide Field Camera 3, or WFC3, one of Hubble's most capable instruments. Over the course of 6 hours, WFC3 captured the comet in visible and near-infrared light, building up a detailed portrait of its coma, nucleus, and tail. The images arrived at the Space Telescope Science Institute in Baltimore on December 1st. Dr. Zsolt Levay, an imaging specialist who had worked with Hubble data for over 2 decades, processed the raw frames, aligning them, calibrating the colors, removing cosmic ray artifacts. When he saw the final image, he stopped. The comet's coma was enormous. In the visible light frames, the coma extended nearly 40,000 kilometers from the nucleus, a diffuse, glowing cloud of gas and dust. In the infrared, where WFC3 was sensitive to heat and certain molecular emissions, the coma was even larger, nearly 60,000 kilometers, suggesting a thick envelope of warm gas. But it was the structure that caught Levay's attention. The coma wasn't smooth. It was striated, with faint arcs and shells visible in the high-contrast processing, as if the comet were releasing gas in pulses rather than a steady flow. And the tail. There were 2 of them. One tail pointed away from the Sun, as expected, a broad, faint streamer of dust, curving gently as the particles followed their own orbits. But the other tail pointed toward the Sun. It was sharp, narrow, bright, stretching tens of thousands of kilometers in the anti-solar direction, the wrong direction. Levay checked the alignment, re-ran the processing, double-checked the date and the comet's position. No mistake. 3 Atlas had an anti-tail. Anti-tails are rare, but not unknown. They're optical illusions, usually caused by edge-on views of the comet's dust sheet, a thin plane of particles that the comet sheds as it moves. When Earth's viewing angle lines up with that plane, the sheet appears as a line pointing toward the Sun. But they're supposed to be faint, diffuse, short-lived. This one was none of those things. It was bright. It was coherent. And based on the Hubble images, it had persisted for at least 6 hours, showing no sign of fading or dispersing. LeVay sent the images to Dr. Nalan Samarasinha, a comet dynamicist at the Planetary Science Institute, who had studied anti-tails for most of his career. Samarasinha received the images on December 2nd and immediately ran a geometric model. For an anti-tail to look that sharp and that bright, the dust sheet had to be remarkably thin, less than 1,000 kilometers thick, and remarkably dense, with particle sizes skewed toward larger grains that reflected sunlight efficiently. But here was the problem. 3I Atlas's dust production was low. The gas-to-dust ratio was roughly 10-to-1, meaning most of what the comet was releasing was gas, not dust. So where was all this dust coming from? Samarasinha ran the numbers again, testing different assumptions. Maybe the dust was older, left over from an earlier outburst. Maybe the particles were unusually large, taking longer to disperse. Or maybe, he noted in his report, the dust wasn't behaving according to standard dynamics. He flagged it as anomaly number 4. Meanwhile, 41 million miles away, another set of eyes was watching. The Jupiter Icy Moons Explorer, JUICE, is ESA's flagship mission to the outer solar system, launched in April 2023, and currently en route to Jupiter, where it will spend years studying Europa, Ganymede, and Callisto. But in late November 2025, JUICE was passing through the inner solar system on a gravity-assist trajectory, using Earth and Venus flybys to build up speed for the long journey ahead. And on November 30th, JUICE happened to have a clear line of sight to 3I Atlas. Dr. Olivier Waites, JUICE's project scientist at ESA, had requested a brief observation window using the spacecraft's high-resolution camera and plasma instruments. The geometry was perfect. From JUICE's vantage point, 3I Atlas was nearly 90 degrees offset from Earth's view, offering a completely different perspective on the coma and tail. The observation ran for 12 hours on November 30th and December 1st, with JUICE's cameras capturing visible light images, while its particle detectors measured the plasma environment. The images arrived at ESA's Operations Center in Darmstadt, Germany, on December 3rd. Dr. Waites reviewed them with his team. From JUICE's perspective, the comet's coma looked stretched, elongated, as if the gas was streaming preferentially in one direction. The anti-tail, so prominent in Hubble's images, was barely visible from JUICE's angle, just a faint smudge near the nucleus. But there was something else. JUICE's plasma instruments had detected a faint, structured signal in the magnetic field around the comet, a perturbation, a ripple in the background interplanetary field. It was subtle, barely above the noise threshold, but it was there. Comets don't have intrinsic magnetic fields. They're not large enough, not geologically active enough, to generate dynamos like Earth or Jupiter do. But they can interact with the solar wind's magnetic field, dragging and distorting it as ionized gas from the coma gets picked up by the wind and carried away. That's what JUICE was seeing, a comet-solar wind interaction, a standard phenomenon. But the structure of the perturbation was unusual. Dr. Waites sent the data to Dr. Jones at University College London, who had been tracking the comet's plasma behavior since perihelion. Jones compared the JUICE data with models of typical comet magnetotails. Normal comets produce broad, diffuse magnetotails that stretch downwind for millions of kilometers, blending into the background solar wind. 3I Atlas's magnetotail, based on JUICE's measurements, was narrow and coherent, almost filamentary. "It's like a wire," Jones said in a call with Waites. "A wire embedded in the solar wind." Waites asked the obvious question, "Is that normal?" Jones hesitated. "Rare," he said. "But maybe not abnormal. We'd need more data." They flagged it for follow-up. By December 5th, the two datasets, Hubble's optical images and JUICE's plasma measurements, were being analyzed side by side. Dr. Meach coordinated a joint working group, bringing together imaging specialists, plasma physicists, and dynamicists to integrate the observations. The picture that emerged was complex. 3I Atlas was releasing gas asymmetrically, with jets or active regions concentrated on one hemisphere of the nucleus. That explained the coma's striated structure and the elongation JUICE had seen. The dust was being released in pulses, not continuously, which explained the anti-tail's unusual brightness and coherence. And the plasma environment around the comet was more structured than expected, possibly because the comet's rotation or outgassing pattern was creating a periodic modulation in the ionization rate. It all fit, barely, but the margins were tight. Every explanation required assumptions that pushed the boundaries of standard comet models. Dr. Meech sent a summary to the Observation Campaign Slack channel on December 6th. Her message was short. "We're seeing something we've never seen before. I don't know if that means it's new physics or just a weird comet. Either way, December 19th matters a lot." The channel went quiet for a few minutes. Then the replies started coming in. "We'll be ready. Locked in. Let's not miss this. Out here, nothing is random." Chapter 6. December 1st, Methanol, Cyanide, and the Chemistry of Life Between Stars. Chemistry is a universal language. Carbon bonds to hydrogen. Oxygen seeks electrons. Under the right conditions, cold, dense clouds of gas and dust lit by starlight, simple molecules assemble themselves into more complex structures. Methanol, formaldehyde, glycine, the building blocks of proteins, sugars, nucleotides. Life, as we know it, is chemistry. And chemistry crosses boundaries. On December 1st, 2025, the Atacama Large Millimeter Submillimeter Array, ALMA, turned its 66 radio dishes toward 3 Atlas. ALMA sits at 5,000 meters elevation in the Chilean desert, where the air is so dry and thin that it's nearly transparent to millimeter wavelength radio waves. This is the regime where molecules shine, emitting faint radiation as they rotate and vibrate in the cold vacuum of space. ALMA is designed to see those emissions. And on December 1st, after weeks of scheduling, calibration, and weather delays, ALMA got its first clean look at 3 Atlas's coma. The observation ran for 6 hours, covering multiple molecular transitions, spectral lines corresponding to specific chemicals at specific temperatures. The data was processed overnight at ALMA's Array Operations Site and transmitted to partner institutions in North America, Europe, and Asia. Dr. Clara Nguyen at MIT received the first spectra on the morning of December 2nd. She opened the file and scrolled through the emission lines. Carbon monoxide. Strong, as expected. CO is one of the most abundant molecules in comets, second only to water. Hydrogen cyanide. Present, also expected. HCN is a common cometary molecule, toxic to humans but essential in prebiotic chemistry. Water vapor. Detectable, though weaker than the CO, consistent with previous observations. And methanol. A lot of methanol. Nguyen zoomed in on the CHO emission line at 304 GHz. The signal was bright, clean, well above the noise. She ran a quick calibration to convert the line intensity into a production rate. The result, methanol accounted for approximately 8% of 3A Atlas's total gas output. She ran the calculation again, checking for errors. Same result. 8%. In most solar system comets, methanol hovers around 1% to 2% of the total volatile budget. A few rare comets, like C. 1996, B2 Hyakutake, have shown methanol fractions as high as 4%. But 8%? Nguyen cross-referenced the literature. She found 3 papers describing methanol-rich comets, but none with fractions above 5%. 3 Atlas was off the chart. She sent the spectrum to Dr. Stephanie Millam, an astrochemist at NASA Goddard, who had worked on the James Webb Space Telescope's observations of solar system comets. Millam looked at the data and immediately understood the implications. Methanol is a tracer of formation environment. It forms in cold, dense regions where carbon monoxide ices stick to dust grains and get hydrogenated, combined with hydrogenate atoms through surface chemistry. The colder the environment, the more efficient the process. A methanol fraction of 8% meant 3 Atlas had formed in a very cold place. Colder than the outer solar system. Colder than the Kuiper belt. Maybe as cold as 20 Kelvin, negative 253 degrees Celsius, typical of the dense cores of interstellar molecular clouds. This thing formed in deep space, Milam said in a video call with Nguyen on December 3rd. Not around a star, not in a protoplanetary disk, in a cloud. Nguyen nodded. Or in a disk that was unusually cold. A disk around a dim star, maybe a red dwarf. Milam pulled up a star chart. If it came from Cassiopeia, there are hundreds of red dwarfs in that direction. They sat in silence for a moment. Then Nguyen said, "What if it's not just about where it formed? What if it's about what it's carrying?" She pulled up a second emission line. Hydrogen cyanide, HCN. HCN is one of the most important molecules in origin of life research. In lab experiments, HCN can polymerize, link into chains, to form adenine, one of the nucleotide bases in DNA. It's also a precursor to amino acids, the building blocks of proteins. The ALMA data showed HCN at about 0.5% of the total gas output, right in the range expected for a typical comet. But combined with the high methanol abundance, the chemistry started to look interesting. Nguyen ran a simulation, modeling what would happen if you took methanol, hydrogen cyanide, water, and carbon monoxide, the four most abundant species in 3 Atlas's coma, and exposed them to ultraviolet light and cosmic rays over millions of years. The result? Formaldehyde, glycolaldehyde, amino acids, and a host of more complex organics. In other words, the raw materials for life. Milam reviewed the simulation. So 3I Atlas is like a chemistry lab. A traveling synthesis reactor. Wendeli. Nguyen nodded. And it's been running for hundreds of millions of years, maybe longer. The implications were profound. If interstellar comets like 3E Atlas carried prebiotic chemicals across the galaxy, they weren't just rocks. They were messengers. Vehicles for distributing the chemistry of life between star systems. Panspermia. The idea that life's building blocks could be transferred between planets, even between stars, had been a fringe hypothesis for decades. But if every star system produced objects like 3I Atlas, and if those objects wandered the galaxy for millions of years, enriched with organics, then panspermia wasn't fringe. It was inevitable. On December 4th, Nguyen drafted a paper outlining the findings. She titled it, High Methanol Abundance in Interstellar Comet 3I Atlas. Implications for Prebiotic Chemistry in the Galaxy. She sent it to Milam and a handful of collaborators for review. One of them was Dr. Avi Loeb. Loeb read the draft that evening and sent a reply the next morning. "This is important," he wrote. "But you're stopping too soon. If the chemistry is this rich, why assume it's all natural?" Nguyen frowned at the screen. Loeb continued, "Methanol is also a fuel. HCN is used in industrial chemistry. If you were designing a propulsion system for an interstellar probe, you'd want a compact, energy-dense fuel and a versatile chemical feedstock. This inventory fits." Nguyen read the message twice. She knew where Loeb was going. He had been arguing for years that Oumuamua might have been a light sail, and that interstellar objects should be scrutinized for technosignatures, evidence of engineering, not just natural processes. But she also knew the response that argument would provoke. On December 5th, Dr. Paul Weissman, the Comet veteran, published a blog post preemptively pushing back against speculation masquerading as science. He didn't name Loeb directly, but he didn't have to. "Comets are natural objects," Weissman wrote. "They form naturally. They outgas naturally. Unusual chemistry doesn't mean artificial. It means we have more to learn about how the universe makes comets." The debate was playing out in real time, in overlapping Slack channels, ArcSefi preprints, and Twitter threads. Some researchers sided with Weissman. Keep it simple, keep it natural, don't jump to exotic conclusions. Others sided with Loeb. Keep an open mind, test all hypotheses, don't rule anything out just because it's uncomfortable. And a third group, including Nguyen and Milam, sat somewhere in between. They didn't think 3I Atlas was a probe. They thought it was a comet. But they also thought the chemistry was remarkable, that it told a story about the galaxy's ability to synthesize and transport complex molecules, and that dismissing it as just a comet missed the point. On December 6th, Nguyen added a paragraph to her paper, carefully worded. While we interpret the methanol-rich composition of 3E Atlas as a product of natural formation in a cold interstellar environment, we note that such chemistry is also of interest to astrobiology and, in principle, could serve as a resource for hypothetical technological systems. Further observations are needed to distinguish between these possibilities. She submitted the paper to the Astrophysical Journal that afternoon. It would be published 3 weeks later and cited more than 200 times in the first month. But by then, December 19th would have come and gone, and the conversation would have moved on. Out here, nothing is random. Word count check. 13,600 words so far. Continuing to Chapter 7. Chapter 7. December 3rd. Planetary defense rehearses for a threat that isn't there. Planetary defense is a strange profession. You train for events that haven't happened. You write protocols for scenarios that might never occur. You run drills simulating disasters, knowing that if you do your job right, the public will never hear about them. And when a real object appears, not a threat, but close enough to practice with, you don't waste the opportunity. On December 3rd, 2025, NASA's Planetary Defense Coordination Office initiated exercise Cosmic Sentinel, a week-long simulation using 3I Atlas as a live test case. The scenario was simple. Assume, hypothetically, that 3A Atlas was on a collision course with Earth. How would the Planetary Defense Network respond? The exercise wasn't about moving the comet. It couldn't be moved. It wasn't a threat. The exercise was about communication, decision-making, coordination across agencies and nations. Could astronomers track the object accurately enough to predict an impact zone? Could space agencies calculate and implement a deflection mission? Could governments agree on who would launch, who would pay, who would lead? Could the public be warned without triggering panic? Dr. Lindley Johnson, NASA's Planetary Defense Officer, laid out the goals in a briefing document circulated to partner agencies in early December. This is not a drill in the traditional sense. It's a live-fire exercise using a real object. We won't be launching anything. We won't be evacuating anyone. But we will be testing every step in the decision chain, from detection to deflection, as if this were real. The participants included NASA, ESA, JAXA, Roscosmos, the European Space Agency, the United Nations Office for Outer Space Affairs, the U.S. Department of Defense, and a dozen smaller agencies. The first day, December 3rd, was dedicated to detection and tracking. Simulated alerts were issued. Observatories were tasked with providing updated orbital elements. Radar facilities were asked to estimate the object's size, rotation, and composition. In reality, all of this had already been done. 3 Atlas's orbit was known to high precision. Its size was estimated at 2 to 4 kilometers. Its rotation period, based on light curve data, was about 16 hours. But the exercise asked, what if we didn't know? What if this object had been discovered only days ago, with minimal tracking data? Teams scrambled to simulate that uncertainty, introducing artificial errors into the orbital model and asking participants to refine it under time pressure. Dr. Torres at JPL led the tracking simulation. His team used a degraded version of 3 Atlas's orbit, stripped of the high-precision measurements, and asked participants to discover the correct trajectory using only simulated observations. It took 3 days. In a real scenario, with a real impact threat, 3 days could be the difference between evacuation and catastrophe. Torres filed a report. Current network response time is too slow for short warning scenarios. Recommend investment in rapid response, automated tracking. The second phase of the exercise, beginning December 6th, focused on deflection. Assuming the orbit was known, and assuming an impact was imminent, what could be done? The answer depended on lead time. If you had years, you could launch a kinetic impactor, a spacecraft designed to ram the asteroid and change its velocity by a few centimeters per second. That's what NASA's DART mission had tested in 2022, successfully altering the orbit of the asteroid Dimorphos. If you had months, you could attempt a gravity tractor, a spacecraft that hovers near the asteroid using its own gravitational pull to tug the object off course. Slow, gentle, inefficient, but theoretically possible. If you had weeks? Nuclear. A nuclear explosive detonated near, not on, but near, an asteroid could vaporize surface material, creating a rocket-like thrust that pushed the object onto a different trajectory. It was controversial. It was dangerous. It required international agreements that didn't yet exist, but it was the only option for short warning, high-consequence impacts. Exercise Cosmic Sentinel walked through the nuclear scenario in detail. Who would authorize the launch? The United States and Russia were the only nations with nuclear weapons mounted on rockets capable of reaching deep space. But would either country act unilaterally? Would the UN Security Council need to approve? What if the impact zone was contested territory? What if the deflection mission accidentally caused the asteroid to hit a different country? The simulation posed these questions to real policymakers, in real time, through video conferences and secure chat channels. The results were messy.com. On December 7th, the U.S. delegation proposed launching a nuclear deflection mission within 72 hours using a modified Delta heavy rocket. The Russian delegation objected, arguing that unilateral action violated the Outer Space Treaty. The European Union delegation proposed waiting for further analysis. China's delegation didn't respond for 6 hours. By the time consensus was reached, a joint US-ESA mission, pending UN approval, the simulated impact window had already passed. In the scenario, the asteroid hit Earth. Impact zone. The North Atlantic Ocean, approximately 800 miles east of Newfoundland. Simulated casualties, 0, due to the oceanic impact. Simulated damage, tsunamis affecting coastal regions of Canada, the US, and Western Europe. Estimated economic impact, $200 billion. In the real world, 3A Atlas passed Earth harmlessly on December 19th, 170 million miles away. But the exercise revealed uncomfortable truths. Dr. Johnson's after-action report, filed on December 10th, was blunt. Our detection capabilities are improving, but our decision-making infrastructure is not. We can see threats earlier than ever before, but we cannot agree on how to respond. Until that changes, detection alone is insufficient. Until that changes, detection alone is insufficient. The report was classified, but portions were leaked to the press by December 12. Journalists framed it as a failure. NASA drill shows US unprepared for asteroid threat. No. Defense officials pushed back. Exercise identifies areas for improvement, not failure. The public, largely unaware that 3E Atlas was being used as a test case, reacted with a mix of alarm and indifference. A few noticed the comet's name in the fine print of the NASA briefing documents and started asking questions online. Wait, they're practicing on the Interstellar comet? Why would they use 3E Atlas for a defense drill? Is there something they're not telling us? This is either really smart or really suspicious. NASA issued a clarification on December 13th. 3. Atlas poses no threat to Earth. Its use in Exercise Cosmic Sentinel is purely for training purposes. The object's interstellar origin makes it an ideal test case for multi-agency coordination. The statement diffused most of the speculation, but not all of it. Behind the scenes, a quieter debate continued. If 3A Atlas had been a threat, if its orbit had been different by just a few degrees, how would they have responded? And if the next interstellar object wasn't benign? Dr. Torres ran a simulation on his own time, late at night, on December 13th, after the exercise had officially ended. He took 3 Atlas's actual orbit and tweaked it. Not much. Just a 5-degree shift in inclination, a slightly lower perihelion. The new trajectory intersected Earth's orbit on December 19th. Impact probability, 12%. He stared at the screen. 12%. 1 in 8. Not likely, but not negligible. And in his simulation, the warning time was 4 months, from the July discovery to the December impact window. 4 months to build consensus, design a mission, launch a spacecraft, intercept the object. Could they do it? Taurus didn't think so. He saved the simulation and closed his laptop. Then he sat in the dark, thinking about how thin the margins really were. Out here, nothing is random. Chapter 8, December 6th, the 16.16-hour heartbeat. Light curves are the chronicles of spinning worlds. Every object in space that isn't perfectly spherical, and nothing is perfectly spherical, reflects sunlight unevenly as it rotates. Bright side, dark side. Bright again. If you measure that object's brightness over time and plot the results, you get a light curve, a graph of brightness versus time, a visual heartbeat. Most asteroids produce choppy, irregular light curves, full of sharp peaks and troughs that reflect their lumpy, cratered shapes. Comets, with their jets and outgassing, produce messier curves, complicated by dust and gas that obscure the nucleus. But some objects produce clean, periodic light curves, smooth, rhythmic, predictable. 3I Atlas was one of them. On December 6th, Dr. Raoul Barrand, an astronomer at the Geneva Observatory who runs the Courbes de rotation d'astéroïdes project, a database of asteroid light curves, received a data package from an international collaboration of small telescope observers. 27 amateur and professional astronomers, spread across 6 continents, had been tracking 3 Atlas since mid-November, taking photometric measurements every clear night. Individually, each observer's data was noisy, incomplete, full of gaps caused by weather and daylight. But combined, the data sets overlapped, filling in the gaps, creating a nearly continuous light curve spanning 3 weeks. Barron loaded the data into his analysis software and ran a period-finding algorithm, a mathematical tool that searches for repeating patterns in noisy data. The result came back immediately. Period. 16 60 hours, down to 4 hours. Amplitude. 0.3 magnitudes, roughly a 30% variation in brightness. Confidence. 99.7% poids. Barron stared at the plot. The light curve was clean. Almost suspiciously clean. It showed a double peak structure, 2 maxima and 2 minima per cycle, separated by roughly 8 hours. That suggested the comet's nucleus was elongated, roughly twice as long as it was wide, tumbling end over end as it moved through space. Standard interpretation. 3I Atlas was a rotating irregular body, shaped like a potato or a dumbbell, with jets or active regions on opposite sides that enhanced the brightness variations. But there was something odd about the period itself. 16.6 hours. That was fast. Not record-breaking fast. Some small asteroids spin in minutes, but faster than most comets. Most cometary nuclei rotate with periods between 24 and 72 hours. Slower than that, and you start wondering if tidal forces or outgassing torques have slowed them down. Faster, and you start wondering what's spinning them up. Barron sent the light curve to Dr. Nalan Samarasinha, who had been studying cometary rotation for decades. Samarasinha reviewed the data on December 7th. His first instinct was that this was a normal rotational light curve, complicated slightly by the comet's outgassing. But then he noticed something. The period was constant. Over 3 weeks of observation, from late November through early December, the light curve's period hadn't changed. Not by a minute. Not by a second. That was unusual. Comets, especially active comets releasing a lot of gas, experience torques. Those torques change the rotation rate over time, speeding the comet up or slowing it down. It's called non-principal axis rotation, and it's messy. The light curve shifts, the period drifts, the amplitude changes. But 3I Atlas's light curve was locked in. 16.6 hours, steady as a metronome. Samarasinha ran a model to estimate how much torque the comet's outgassing should be producing, based on the observed gas production rate and the likely geometry of the jets. The answer: enough to change the rotation period by about 0.5% over 3 weeks. That should have been detectable in the data. But it wasn't there. He ran the numbers again, testing different assumptions. Maybe the jets were symmetrically placed, canceling out each other's torques. Maybe the nucleus was spinning around its principal axis, which would stabilize the rotation. Possible. Barely. Or maybe something else was stabilizing it. He didn't like where that thought led, so he filed it away and sent a report to Berend. Clean light curve. Unusually stable period. Recommend continued monitoring. Meanwhile, on December 8th, Dr. Beatrice Miller, a planetary scientist at DLR, the German Aerospace Center, received the same light curve data and had a different reaction. Mueller specialized in the dynamics of small bodies, particularly how they evolved over time under the influence of impacts, outgassing, and tidal forces. She looked at 3 Atlas's 16.6-hour period and thought, that's a resonance. Resonances are special numbers. They occur when two processes, rotation and orbit, or rotation and outgassing, or rotation and tidal forces, sync up, locking into a stable relationship. Earth's moon is in a 1-1 resonance with its orbit, which is why the same side always faces Earth. Pluto and its moon Charon are mutually tidally locked, each showing the same face to the other. Resonances are common in the solar system. They're signs of long-term stability, places where chaos gives way to order. Mueller ran a calculation. If 3 Atlas's rotation period was 16.16 hours, and if it had been rotating at that rate for a long time, was it in resonance with anything? She tested a few possibilities. Resonance with its orbital period? No. The orbital period was measured in months, not hours. Resonance with outgassing pulses? Maybe, but that required the jets to fire in a repeating pattern that matched the rotation, which seemed circular. Resonance with something else? She didn't find an answer, but she flagged the period as noteworthy in her notes. On December 9th, the light curve data was posted to a public Slack channel for the 3 Atlas observation campaign. Dr. Avi Loeb saw it within hours. He pulled up the plot and studied it for a long time. Then he sent a message to the channel. 16.60 hours. Clean, stable, double-peaked. Question. How many natural processes produce light curves this regular? Replies came quickly. Lots. It's just rotation. Agreed. This is standard cometary behavior. Nothing unusual here. Loeb waited a few minutes, then sent a follow-up. True. But if you wanted to encode a signal in a light curve, a stable periodicity would be the simplest method. Just a thought. The channel went quiet. Then someone replied, Avi, not everything is a technosignature. Another. This is a comet. Comets rotate. That's what they do. Loeb didn't respond immediately. But later that day, he published a blog post on Medium titled The Heartbeat Hypothesis. In it, he outlined a thought experiment. Suppose an advanced civilization wanted to mark an object for detection by other civilizations. They couldn't rely on radio signals. Those fade over interstellar distances. They couldn't rely on surface markings. Those erode under cosmic rays and impacts. But they could engineer a stable rotation, a periodic brightness variation that would persist for millions of years and be detectable from light years away. All you'd need was mass distribution, internal structure that resisted torques, and a slight offset in the center of mass. 16.16 hours wasn't arbitrary, Loeb wrote. It was short enough to be measured quickly by any civilization with telescopes, but long enough to be stable against perturbations. He didn't claim 3 Atlas was artificial. He claimed it was worth checking. The post was shared 15,000 times in 24 hours. Responses ranged from thoughtful to scathing. Loeb is a brilliant scientist letting his imagination run wild. This is why we need skeptics. Extraordinary claims, extraordinary evidence. But what if he's right? Dr. Mueller, reading the blog post on December 10th, felt a strange unease. She didn't think 3 Atlas was a probe, but she couldn't shake the feeling that the light curve was too clean. On December 11th, she ran one more calculation. If you wanted to design an object to produce a stable, periodic light curve, what would it look like? Answer: a cylinder or a dumbbell rotating around its short axis with internal mass symmetry. She modeled it. A 3-kilometer-long object, density roughly 500 kg/m, typical for icy bodies, rotating every 16.6 hours. The model worked. It produced a light curve almost identical to what they were seeing. But so did a dozen other natural shapes. She saved the simulation and closed her laptop. Then she sat in silence, thinking about coincidences, and how many you could stack before they stopped being coincidences. Out here, nothing is random. Chapter 9. December 9th. The anti-tale that shouldn't exist. Dust doesn't lie. It doesn't have opinions, doesn't care about theories, doesn't bend to human expectations. Dust obeys physics, gravity, radiation pressure, solar wind drag. You can model its motion with precision, predict where it should be, how bright it should look. And when it doesn't match the model, it's telling you something. On December 9th, Dr. Zsolt Levay at the Space Telescope Science Institute received new Hubble images of 3E Atlas, captured 48 hours earlier as part of the ongoing observation campaign. The images were stunning. DUFC-3 had imaged the comet in 3 bands, visible, near UV, and near ear, building up a high-contrast color composite view of the coma and tail. The main dust tail was there, broad and diffuse, arching away from the sun in a gentle curve, exactly as expected. But the anti-tail was brighter. Levay zoomed in. The sunward-pointing spike, first noticed in the November 30th images, was still present, and it had grown. In the earlier images, the anti-tail had stretched perhaps 20,000 kilometers. Now, it was closer to 40,000 kilometers, a sharp, bright line pointing almost directly at the sun, cutting through the coma like a needle. Levay ran the enhancement pipeline again, checking for artifacts, cosmic rays, diffraction spikes, scattered light. Nothing. The feature was real. He sent the images to Dr. Samarasina with a message. "Your anti-tail just doubled in length. Thoughts?" Samarasina opened the files on December 10th and swore quietly. Anti-tails are supposed to be transient. They're caused by edge-on views of a comet's orbital dust plane, a thin sheet of particles left behind as the comet moves. When Earth's line of sight aligns with that sheet, it appears as a spike. But that alignment lasts hours, maybe days. As the comet moves and the viewing geometry changes, the anti-tail should fade, spread out, disappear. 3 Atlas's anti-tail wasn't fading. It was growing. Samarasina ran a new model, updating the comet's position, velocity, and viewing angle. The geometry was still favorable for an anti-tail, but only barely. By December 9th, Earth's viewing angle had shifted by several degrees. The dust sheet should have been tilting out of alignment. Yet the anti-tail was brighter than ever. He tested a hypothesis. Maybe the dust sheet was unusually dense, with enough particles to remain visible, even at a tilted angle. But the numbers didn't work. To produce an anti-tail that bright at that geometry, the comet would need to be releasing dust at a rate 10 times higher than observed. He tested another hypothesis. Maybe the anti-tail wasn't an edge-on sheet. Maybe it was a physical structure, a jet of dust being actively expelled toward the sun. But that violated basic physics. Radiation pressure pushes dust away from the sun. Solar wind drags it outward. There's no natural force that would create a sustained sunward-pointing jet. Samarasina sent a note to Dr. Geraint Jones at UCL. "I need plasma physics. Something weird is happening with this tail." Jones received the Hubble images and the viewing geometry data on December 11th. He spent the next 2 days running simulations of the comet's plasma environment, the charged particles in the coma, and how they interacted with the solar wind's magnetic field. His model showed something unexpected. If the comet was releasing a lot of ionized gas, which it was, and if that gas was unusually cold and dense, which spectroscopy suggested it might be, then the solar wind's magnetic field could wrap around the coma in a complex, twisted structure. Under the right conditions, charged dust grains could get trapped in that structure, held in place by magnetic forces rather than blown away by radiation pressure. The result, a narrow filamentary dust feature pointing in directions that standard models wouldn't predict. Jones called it a magnetic dust tail. It wasn't unprecedented. Some comets showed hints of similar features, faint and poorly understood. But 3I Atlas's anti-tail was bright, coherent, and persistent, far more pronounced than anything seen before. Jones sent his simulation to Samarasina with a note. This works. Barely. Once. But it requires the plasma environment to be much more structured than normal. I don't know why it would be. Samarasina reviewed the simulation and agreed. It explained the observations, but only if you assumed the comet was doing something unusual with its ionized gas output. He flagged it as anomaly number 5. Meanwhile, on December 10th, radio astronomers at the Very Large Array in New Mexico had been tracking 3 Atlas in the centimeter wavelength regime, looking for emissions from charged particles in the coma. The VLA isn't designed for comet observations. Its primary mission is studying distant galaxies and quasars. But Dr. Rachel Webster, a radio astronomer at the University of Melbourne, had requested a brief observation window to test whether 3 Atlas was producing detectable synchrotron emission, radiation generated when electrons spiral in magnetic fields. Most comets don't produce synchrotron emission. Their magnetic environments are too weak. But 3I Atlas, with its rich gas output and structured plasma tail, might be different. The Veil observation ran for 4 hours on December 10th, integrating signal over multiple frequencies to build up sensitivity. The data arrived on December 12th. Webster processed it and found a faint, but statistically significant, signal at 6 GHz, a detection of synchrotron emission from the comet's coma. She ran the numbers. The emission was weak, corresponding to a magnetic field strength of about 10 nanotsla, roughly 100 times weaker than Earth's surface field, but unusually strong for a comet. The source of the field was the draped interplanetary magnetic field, wrapped and compressed by the comet's outgassing. But the structure of the emission was odd. Instead of a smooth, diffuse glow, the VLA data showed a narrow, elongated feature, consistent with a filamentary magnetic structure. Webster sent the data to Jones with a note. Your magnetic dust tail has a radio signature. This is real. Jones reviewed the VLA data and updated his model. The picture that emerged was strange, but self-consistent. 3I Atlas was releasing unusually cold, dense, ionized gas. That gas interacted with the solar wind, creating a twisted, filamentary magnetotail. Charged dust grains got trapped in that magnetotail, forming a coherent sunward-pointing structure that looked like an anti-tail but was actually a magnetic artifact. It all fit. But it required the comet to be outgassing in a very specific way. Cold, dense, ionized, structured. Why? Jones didn't have an answer. He sent a summary to the Observation Campaign's working group on December 13th, concluding with a carefully worded statement. The observed anti-tail can be explained by natural plasma dust interactions, provided the comet's outgassing is unusually structured. We do not currently understand what drives that structure. Dr. Meach, reading the report, added it to the growing list of things they needed to figure out by December 19th. On December 14th, Dr. Alvy Loeb posted another blog entry, this time with the headline, When Tails Point the Wrong Way. In it, he reviewed the anti-tail observations and Jones's magnetic dust tail hypothesis. He agreed it was a plausible explanation, but he also noted that magnetic fields could be engineered. A sufficiently advanced technology could generate structured fields, manipulate plasma, control dust trajectories. I'm not saying this is artificial, he wrote. I'm saying we should be asking whether it could be, and what observations would test that. He proposed a simple experiment. Use radar to measure the anti-tail's physical structure. If it was a natural dust sheet, radar would show a broad, diffuse return. If it was a filamentary structure, radar would show something narrower, more coherent. The proposal was sent to NASA's Jet Propulsion Laboratory and the Arecibo Observatory's successor facilities. But by then, Arecibo was gone, collapsed in 2020, and the remaining planetary radar systems were already overbooked. The test wouldn't happen. At least, not for 3. On December 15th, Samarazina sat in his office, staring at the Hubble images. 2 tails. One pointing away from the sun, one pointing toward it. One made of dust following ballistic trajectories, one made of charged particles trapped in magnetic fields. Natural. Probably. But undeniably strange. He thought about Oumuamua, how its acceleration had never been fully explained, how the debates still raged years later. He thought about 3 Atlas, how every anomaly had an explanation, but how those explanations kept piling up, each one requiring the comet to be doing something unusual. At what point, he wondered, did it unusual become unprecedented? And at what point did unprecedented become impossible to ignore? He didn't know, but he knew December 19th was 4 days away. Out here, nothing is random. Word count check, 820,100 words. Continuing to final chapters. Chapter 10, December 12th, Stacking the Odds, Rock, Relic, or Relic Technology. Probability is a strange currency in science. It lets you quantify uncertainty, measure confidence, compare hypotheses. But it also lets you hide in the comfortable middle, where nothing is ever certain and everything remains possible. By December 12th, 3 Atlas had accumulated enough anomalies that researchers were starting to ask a blunt question. What are the odds this is just a comet? The question wasn't rhetorical. It was mathematical. Dr. Gregory Laughlin, an astrophysicist at Yale, who specializes in planetary dynamics and statistical modeling, took it seriously. On December 12th, he published a preprint on Arxiv titled Bayesian Analysis of Anomaly, Clustering in Interstellar Object 38 Atlas. The paper was dense, technical, filled with equations and probability distributions. But the core argument was simple. Take each observed anomaly. High methanol non-gravitational acceleration, stable 16.16-hour period, magnetic anti-tail, and assign it a probability based on how often similar features appear in solar system comets. Then multiply those probabilities together to estimate the likelihood that all the anomalies would occur in a single object by chance. Laughlin's team started with methanol abundance. In a survey of 50 well-studied solar system comets, only 3 showed methanol fractions above 4% and none above 6%. 3 Atlas was at 8% twice. They assigned a probability, 1 in 50 or 2%. Next, non-gravitational acceleration. About 70% of active comets show measurable non-gravitational forces. But most of those forces point radially outward from the Sun. 3 Atlas's acceleration was tilted, asymmetric. How common was that? In a sample of 30 comets with well-measured non-gravitational accelerations, only 2 showed similarly tilted trajectories. Probability, 2 in 30 or 7%. Next, the light curve. Stable, periodic, double-peaked, with no detectable drift over 3 weeks. In a survey of 40 cometary light curves, about 10 showed double-peaked periodicity. Of those, only 1 showed a period stable to within 1% over similar timescales. Probability, 1 in 40, or 2.5% watched. Finally, the anti-tail. Magnetic dust tails were rare, but not unheard of. Maybe a dozen comets in the historical record had shown features that might have been magnetic in origin, though the evidence was ambiguous. Laughlin's team estimated the probability of a comet producing a bright, persistent magnetic anti-tail at roughly 5%. Now came the multiplication. If the anomalies were independent, if methanol abundance didn't correlate with rotation rate, if non-gravitational forces didn't predict anti-tail structure, then the combined probability was 0.02, 0.07, 0.05, or about 1 in 57,000. Laughlin's conclusion, stated carefully in the paper's abstract, the observed properties of 3 Atlas are individually rare but not impossible. Collectively, they represent a statistically significant deviation from the expected population of natural comets, with a combined probability of approximately 1.75 Hotenchoktat. While this does not constitute evidence of artificiality, it justifies continued scrutiny and expanded observational efforts. The paper was uploaded to Arxiv at 8:00 a.m. Eastern Time on December 12th. By noon, it had been downloaded 3,000 times. By evening, It was trending on academic Twitter. Responses came fast. Dr. Paul Weissman, the comet veteran, posted a thread critiquing the methodology. Laughlin's analysis assumes independence, but cometary properties are correlated. High methanol might cause unusual outgassing, which might cause non-gravitational acceleration. You can't just multiply probabilities. This is statistical sleight of hand. Dr. Karen Meek, usually cautious, posted a more measured reply. Laughlin raises valid questions. Whether 1 in 57,000 is meaningful depends on sample size and selection effects. But the clustering of anomalies is real, and it deserves investigation. Now, Dr. Avi Loeb, predictably, was enthusiastic. This is exactly the kind of analysis we need. Extraordinary claims require extraordinary evidence, but extraordinary data also requires extraordinary attention. The debate spilled into mainstream media. The New York Times ran a piece on December 13th. Is the interstellar comet just a comet? Scientists aren't sure. Nesinanio, Diwasi. Ars Technica published an explainer. The probability paradox. How rare is too rare to be natural? Wired interviewed Laughlin directly, asking the question everyone wanted, answered. Do you think 3I Atlas is artificial? Laughlin's response was careful. I think it's statistically unusual. That could mean we're missing something about how natural comets work. Or it could mean we're seeing something we haven't seen before. The December 19th observations will help narrow that down. But privately, in emails shared with a handful of colleagues, Laughlin was less cautious. I don't know what this thing is, he wrote. But if I had to bet, I'd say we're looking at an object that doesn't fit our models. Whether that means new kind of comet or something else entirely, I can't say, but the odds are shifting. Meanwhile, at the SETI Institute in Mountain View, California, Dr. Natalie Cabral, an astrobiologist and director of the Carl Sagan Center, was having a different conversation. Cabral had spent her career studying extreme environments on Earth and Mars, looking for signs of life in places where life shouldn't exist. She was trained to think about biosignatures, technosignatures, and the fine line between the two. On December 13th, she convened a small, informal workshop, Interstellar Objects as Astrobiology Targets. The premise, whether or not 3A Atlas was artificial, it was scientifically valuable as a sample from another star system. Think of it as a free sample return mission, Cabral said in her opening remarks. We didn't have to launch anything. We didn't have to wait decades for a flyby. The object came to us, carrying chemistry, structure, maybe even organics that formed around a different star. The workshop participants, astrobiologists, chemists, planetary scientists, spent the day exploring what 3I Atlas could teach them. One session focused on methanol and hydrogen cyanide, and whether those molecules, preserved in ice for millions of years, could retain information about the environment where they form. Another session explored the possibility of amino acids, or more complex organics embedded in the comet's nucleus, and whether Earth-based telescopes could detect them remotely. A third session, more speculative, asked, if the comet was artificial, what would that mean for the search for life? Dr. Jill Tarter, a SETI pioneer and workshop participant, framed it bluntly. If you find a technosignature, you found intelligence. And intelligence implies life. You don't get to skip steps. A probe is a biosignature. The room went quiet. Then someone asked, so what are we looking for on December 19th? Cabral answered, everything. Chemistry, structure, behavior. We're looking for anything that doesn't fit, because the things that don't fit are where the discoveries happen. On December 14th, Dr. Laughlin's paper was formally peer-reviewed and rejected by the Astrophysical Journal. The reviewer's comments were polite but firm. The statistical methodology is sound, but the conclusions are overstated. The authors have not adequately addressed the possibility of correlated anomalies or selection bias. We recommend resubmission with expanded analysis. Laughlin didn't resubmit. Instead, he left the preprint on ArcSIF, where it continued to circulate, cited and debated, a permanent part of the 3I Atlas conversation. On December 15th, Dr. Torres at JPL updated his alignment window simulation one last time. 4 days to go. He looked at the list of instruments scheduled to observe. Hubble, GWST, ALMA, VELTI, Keck, Gemini, JUICE, Vela, and a dozen smaller facilities. He looked at the list of anomalies. Methanol, acceleration, light curve, antitail. He looked at Lafland's probability estimate. 1 in 57,000. And he thought, we're about to find out. Out here, nothing is random. Chapter 11. December 18th, the night before alignment. Anticipation is a kind of gravity. It pulls you forward, collapses time, makes hours feel like minutes and minutes feel like days. By December 18th, the astronomical community was in full anticipatory freefall. December 19th was less than 24 hours away. At the Space Telescope Science Institute in Baltimore, Dr. Zsolt Levay was coordinating Hubble's observation schedule down to the minute. Hubble's time is precious. Every orbit, 96 minutes, pole to pole, is divided into narrow windows when the telescope can point away from Earth, away from the Sun, at targets dim and distant. For December 19th, Hubble had been allocated a 6-hour block for 3I Atlas, spanning 2 orbits. The plan: continuous imaging in visible and near-infrared light, high cadence, overlapping exposures designed to catch any rapid changes in brightness, tail structure, or coma morphology. Levay ran through the sequence one last time, checking pointing coordinates, exposure times, filter wheels. Everything was locked in. At 4:00 AM Eastern Time on December 19th, Hubble would salute to 3I Atlas and begin its observation. The data would download 3 hours later, relayed through NASA's tracking and data relay satellites, processed automatically, and available to the science team by mid-morning. Levay sent a final confirmation email to the observation team. We're go for tomorrow. See you on the other side. Across the Atlantic, at ESA's Operations Center in Darmstadt, Germany, Dr. Olivier Witas was running through a similar checklist for JUICE. The spacecraft was now 45 million miles from Earth, en route to Jupiter, but its trajectory happened to give it a clean line of sight to 3 Atlas on December 19. JUICE's cameras weren't as powerful as Hubble's, but its position, offset from Earth by tens of millions of miles, provided a second viewing angle, a stereoscopic perspective that would help reconstruct the comet's 3-dimensional structure. The observation window was narrow, 8 hours, starting at 6:00 UTC. Witas confirmed the spacecraft's health, checked the instrument status, and sent the final command sequence. JUICE would photograph 3E Atlas 172 times over those 8 hours, 1 frame every 3 minutes. The data would take 24 hours to transmit back to Earth, arriving on December 20th. In Chile, at the ALMA Operations Support Facility, Dr. Clara Nguyen was finalizing the molecular spectroscopy plan. ALMA's observation would run for 10 hours on December 19th, split across 2 sessions to accommodate telescope maintenance and atmospheric calibration. The goal: measure the comet's methanol, hydrogen cyanide, water vapor, carbon monoxide, and any other detectable molecules with unprecedented precision, tracking how the abundances changed over time. If the comet was pulsing, releasing gas in bursts rather than a steady flow, ALMA would see it. Nguyen reviewed the frequency settings one last time, confirming that the correlators were tuned to the right spectral lines. She sent a message to her team. Tomorrow we find out what this thing is made of. Get some sleep. It's going to be a long day. At NASA's Jet Propulsion Laboratory in Pasadena, Dr. Michael Torres wasn't sleeping. He sat in his office at 11:00 p.m. Pacific Time on December 18th, staring at his simulation. The December 19th alignment was a product of geometry. Earth, Sun, and 3I Atlas would form a nearly straight line, with the comet positioned at 1.30 from the Sun and 1.80 from Earth. That alignment maximized the angular separation between the Sun and the comet, as viewed from Earth, making observations easier and reducing contamination from scattered sunlight. But the geometry also meant that Earth-based telescopes and space telescopes would all be looking at roughly the same face of the comet at roughly the same time. If the comet's activity was concentrated on one hemisphere, which the light curve suggested it might be, December 19th would capture that hemisphere at peak visibility. If there was anything unusual, anything hidden, anything waiting to be seen, this was the moment. Torres updated the ephemeris one last time, incorporating the latest positional data from ground-based observatories. The comet's position was known to within a few hundred kilometers. Its velocity was known to within a few meters per second. Everything was aligned. He saved the file and closed his laptop. Then he sat in silence, thinking about Oumuamua one more time. Oumuamua had appeared, puzzled the world, and vanished before anyone could react. 3I, Atlas was giving them a second chance. He wasn't going to waste it. Elsewhere, in observatories scattered across the globe, similar scenes were unfolding. At the Very Large Telescope in Chile, Dr. Helena Rodrigues confirmed her observation window, 4 hours starting at 8:00 UTC, using the forced spectrograph to capture high-resolution spectra of the coma. At the Keck Observatory in Hawaii, Dr. Matthew Knight prepared for infrared imaging, searching for thermal emissions from the nucleus that could constrain its size and surface temperature. At the Very Large Array in New Mexico, Dr. Rachel Webster finalized her radio observation plan, hoping to catch another glimpse of the comet's synchrotron emission and magnetic field structure. And at dozens of smaller observatories, university telescopes, amateur setups, robotic survey systems, astronomers checked weather forecasts, tested equipment, and waited for the sun to set. By midnight UTC on December 19th, the first observations would begin. In Mountain View, California, Dr. Natalie Cabral sat in her office at the SETI Institute, reviewing notes from the previous week's workshop. The question kept circling back. What are we looking for? Chemistry. Structure. Behavior. Anomalies that fit. Anomalies that don't. She thought about the methanol, the antitail, the light curve. She thought about Lafland's 1 in 57,000 estimate. She thought about the careful, measured language scientists used when they didn't want to sound crazy. Unusual, but possibly natural. Statistically significant, but not conclusive. Worth investigating further. Cabral had spent her career in the gray zones, where the line between life and non-life blurred, where chemistry became biology and biology became intelligence. She knew how hard it was to prove something was not natural, and she knew how much harder it was to prove something was. On December 19th, they'd collect data. Terabytes of it. Spectra, images, light curves, magnetic field measurements. And then, over the following weeks, they'd analyze it, compare it, argue about it. But the truth, Cabral knew, might not reveal itself immediately. Sometimes the universe gave you answers. Sometimes it gave you better questions. On the evening of December 18th, Dr. Avi Loeb published one final blog post before the alignment. The title, What We'll Learn Tomorrow and What We Won't. In it, he argued that December 19th was not the end of the story. It was a snapshot, a single moment in time, a narrow slice through a much larger phenomenon. Even if we see something extraordinary tomorrow, he wrote, we'll need follow-up. More observations, more instruments, maybe even a mission to intercept the next interstellar visitor before it leaves. He proposed a concept, a network of rapid-response spacecraft pre-positioned in Earth orbit, ready to launch within days of an interstellar object's discovery. Fast, lightweight, equipped with cameras, spectrometers, and sample return capability. A fleet designed to answer, definitively, what these objects are. We've seen 3 interstellar visitors in 8 years, he wrote. The next one could arrive tomorrow, or next year, or next decade. We need to be ready. The post ended with a single line. December 19th is a test, not of the comet, of us. At 11:59 p.m. UTC, on December 18th, Dr. Torres checked his email one last time. A message from Dr. Meek, sent to the entire observation campaign. Tomorrow matters. Let's make it count. He closed his laptop, turned off the lights, and walked out into the Pasadena night. Above him, invisible to the naked eye, 3I Atlas raced through space at 33 kilometers per second. In 16 hours, it would reach its closest point to Earth, and the world would be watching. Out here, nothing is random. Chapter 12. December 19th. Inside the alignment window. At 4:00 UTC, Hubble woke up. The telescope's guidance system locked onto a trio of reference stars, calculated its orientation to within 1,000th of a degree, and slewed toward coordinates in the constellation Pisces. Target: 3.8 less. Distance: 270 million kilometers. Exposure time: 6 hours. The wide-field camera 3 shutter opened, and photons that had left the comet 8 minutes earlier began landing on the detector, pixel by pixel, building an image. In Baltimore, Dr. Zsolt Levay watched the telemetry stream on his monitor. Pointing stable. Exposure nominal. Data flowing. He exhaled. At 5:47 UTC, as Hubble completed its first orbit, the initial frames downloaded automatically to the Space Telescope Science Institute servers. Levay opened the raw image. The comet was there, centered in the frame, its coma glowing faintly against the black. And the anti-tail, still there. Brighter even than in the December 9th images. Levay ran a quick photometry check, measuring the tail's brightness profile. The sunward spike extended 45,000 kilometers now, nearly 3 Earth diameters, sharp and coherent. He flagged the image for immediate processing and sent a message to the team. Anti-tail confirmed. It's not going away. At 6:0 UTC, ALMA began its first session. The 66 radio dishes in the Chilean desert turned in unison, pointing toward 3 Atlas. Their receivers tuned to the millimeter wavelength emissions of methanol, hydrogen cyanide, and carbon monoxide. Dr. Clara Nguyen monitored the data stream from the operations support facility, watching as spectral lines began to appear on her screen. Methanol. Strong, as expected. Hydrogen cyanide. Present. Stable. Carbon monoxide. Very strong, even stronger than in the December 1st observations. She zoomed in on the methanol line. Something was off. The line was split. Not by much, just a few kilohertz, but unmistakable. A double peak where there should have been a single peak. Nguyen frowned. Spectral line splits can be caused by several things: motion, temperature gradients, multiple gas sources with different velocities. She ran a quick model, testing whether the comet's rotation could produce a split line. Possible. If the comet was releasing methanol from 2 active regions on opposite hemispheres, each with slightly different velocities relative to Earth, the Doppler shift would split the emission into 2 components. But the split was unusually clean, symmetric. She flagged it for deeper analysis and kept watching. At 8:0 UTC, the Very Large Telescope in Chile joined the campaign. Dr. Helena Rodrigues captured a high-resolution spectrum of the coma, using the Force 2 instrument, targeting ultraviolet and visible wavelengths. The spectrum showed water vapor, hydroxyl radical, carbon monoxide, cyanide, all standard cometary molecules. But there was a faint line at 436 nanometers that didn't match anything in the molecular database. Rodrigues ran it through identification software. No match. She checked the calibration, reprocessed the data, double-checked the wavelength solution. The line was still there. She sent the spectrum to Dr. Nguyen with a note. Unidentified emission line. Could be instrumental, could be real. Thoughts? Nguyen received the message at 9:30 UTC and pulled up the spectrum. She stared at the 436 nanometer line. It was faint, barely above the noise, but it was in the right place for ionized carbon, C, a common ion in cometary coma. Except ionized carbon usually emitted at 158 nanometers, in the far ultraviolet. A visible wavelength transition at 436 nanometers would require a different electronic state, a metastable level that was rarely populated under normal condition, unless the gas was unusually cold, or unusually dense, or being excited by something other than sunlight. Nguyen flagged it as anomaly number 6 and added it to the growing list. At 10:0 UTC, JUICE's cameras captured their first clean images of 3 in Atlas from 45 million miles away. Dr. Olivier Vitasse reviewed the frames at ESA's operations center. From JUICE's perspective, the comet's coma looked different, more elongated, stretched along the direction of the sun, as if the gas was streaming asymmetrically. The anti-tail, so prominent in Hubble's images, was barely visible from Juice's angle, just a faint smudge. But there was something new. A second tail, faint and diffuse, pointing perpendicular to both the main dust tail and the anti-tail. Retrace zoomed in. The feature was real, but faint, barely above the detection threshold. He ran a quick model. If the comet was releasing ions that were being picked up by the solar wind and dragged along magnetic field lines, those ions could form a tail that didn't point directly away from the sun. A plasma tail, bent by magnetic forces. Possible. Even expected. But the geometry was odd. The tail's direction didn't match the predicted orientation of the interplanetary magnetic field on December 19. Retrace flagged it for follow-up and sent the images to Dr. Geraint Jones at UCL. Jones received them at 11:00 UTC and immediately started modeling. By 14:00 UTC, he had a preliminary answer. The plasma tail's orientation suggested the local magnetic field around the comet was tilted by about 30 degrees relative to the background solar wind field. That could happen if the comet's ionosphere, the cloud of charged particles in its coma, was dense enough to partially deflect the solar wind, creating a local magnetic environment that didn't match the larger scale field. Unusual but not impossible. Jones sent his analysis to Retrace with a note. This comet is doing everything slightly wrong. Not dramatically wrong. Just off. At 12:00 UTC, halfway through the alignment window, Dr. Torres at JPL compiled the incoming data streams into a single dashboard. Hubble, observing, data clean. ALMA, observing, detecting methanol line split. JUICE, observing, showing asymmetric coma and off-axis plasma tail. VIL, complete, flagged unidentified emission line. VLA, scheduled for 18:00 UTC. KEK, scheduled for 20:00 UTC. The picture was getting more complex by the hour. Torres sent an update to NASA's Planetary Defense Office, observations proceeding nominally. Preliminary data shows continued anomalous behavior across multiple instruments. Full analysis will take weeks. At 15:00 UTC, Dr. Raoul Barrand in Geneva received real-time photometry data from a network of small telescopes that had been tracking 3I Atlas continuously since dawn. The light curve was still clean, still periodic. 16.1 16 hours, 0.02 hours. But there was a new wrinkle. One of the light curve maxima, the brightest point in the cycle, had shifted slightly. Not in timing, but in amplitude. The comet was now 5% brighter at peak than it had been 3 days earlier. Barrand ran a quick calculation. A 5% brightness increase could be caused by increased outgassing, a change in viewing geometry, or a shift in the comet's rotation axis. Or it could be something else. He flagged it and sent the data to Dr. Samarasina. At 18:00 UTC, the Very Large Array in New Mexico began its radio observation. Dr. Rachel Webster watched as the interferometer's antennas combined their signals, building up a radio image of 3I Atlas's coma. The synchrotron emission was still there, faint but detectable, concentrated in a narrow filament aligned with the anti-tail. Webster ran a magnetic field calculation based on the emission's intensity and geometry. The result: 12 nanotesla, slightly stronger than the December 10th measurement. She compared the field structure to models of typical cometary magnetotails. The filament was too narrow, too bright, too coherent. It was the same problem Jones had flagged in early December. This wasn't behaving like a normal comet-solar wind interaction. Webster sent the data to Jones with a note. The magnetic field is getting stronger. I don't know why. By 20:00 UTC, the alignment window was beginning to close. The geometry was shifting. Earth's position, relative to 3I Atlas, and the Sun, was changing, degree by degree, minute by minute. Within hours, the comet would be harder to observe, the angles less favorable, the contamination from scattered sunlight increasing. This was it. The final hours of the best view humanity would ever have of 3 Atlas. At 22:00 UTC, as the last scheduled observations wrapped up, Dr. Karen Meach sent a message to the Observation Campaign Slack channel. Thank you, everyone. We got everything we asked for. Now comes the hard part, figuring out what it all means. Replies came quickly. Incredible data. Can't wait to dig in. This is going to take months to analyze properly. Did we just witness something historic, or just a really weird comet? No one answered the last question. At 23:59 UTC, on December 19th, as the date rolled over to December 20th, Dr. Torres saved his dashboard and closed his laptop. He walked outside, looked up at the sky, and tried to spot 3I Atlas with his naked eye. He couldn't, of course. It was far too faint. But he knew it was there, racing outbound at 33 kilometers per second, carrying with it a cargo of methanol and hydrogen cyanide, a magnetic anti-tail, a 16.16-hour heartbeat, and more questions than answers. And he knew that, by the time the data was fully analyzed, 3 Atlas would be gone. Fading. Irretrievable. Out here, nothing is random. Chapter 13. December 20th. First results, hot takes, and the noise around the signal. The internet moves faster than peer review. By 8:00 am Eastern Time, on December 20th, less than 12 hours after the alignment window closed, the first images and spectra from December 19th were leaking online. Not through official channels. Through Slack screenshots, Twitter posts, Reddit threads. A Hubble image of the anti-tail, watermarked preliminary, do not distribute, appeared on a planetary science Discord server at 7:42 a.m. It was retweeted 800 times in an hour. An ALMA spectrum showing the split methanol line was posted to Arxiv at 9:15 a.m. by a researcher who wasn't listed as a co-investigator on the observation. The post was taken down 20 minutes later, but not before it had been downloaded 1,200 times. By noon, Science, Nature, the New York Times, and BBC News were running stories based on the leaked data, framing December 19th as either a triumph of international collaboration or a deepening mystery, depending on the outlet. NASA issued a statement at 1:00 p.m. Observations of interstellar comet 3I Atlas on December 19th proceeded successfully. Data is currently being analyzed by science teams worldwide. Preliminary results are consistent with a natural cometary origin, though several unusual features remain under investigation. A formal briefing will be held next week. The statement was careful, measured, and almost immediately drowned out by speculation. On Twitter, the hashtag #3Atlas was trending globally by mid-afternoon. Threads ranged from thoughtful to absurd. The antitail is clearly magnetic. Stop saying it's weird. It's just physics. 16.16 hours. That's not random. That's a signal. Wake up. Methanol at 8%? This thing is a fuel depot. It's not a comet. It's a tanker. Nadinalavan. Can we please let scientists do science before we turn this into ancient aliens? YouTube thumbnails appeared, each more sensational than the last. Alien probe confirmed? NASA hiding the truth about 3I Atlas. Interstellar visitor. Natural or technology. Dr. Avi Loeb, unsurprisingly, was invited onto half a dozen podcasts and news programs. On December 20th, he appeared on NPR's Science Friday, where host Ira Flatow asked the question everyone wanted answered. Dr. Loeb, do you think 3I Atlas is artificial? Loeb paused, choosing his words carefully. I think 3I Atlas is worth investigating with the same rigor we'd apply to any potential technosignature. That doesn't mean it is artificial. It means we shouldn't dismiss the possibility out of hand. Science works by testing hypotheses, not by assuming answers. Flatow pressed, but you've seen the data. The methanol, the light curve, the antitail. Does any of that suggest technology to you? Loeb's reply. It suggests something unusual. Unusual enough that we need more data. If we see another interstellar object with similar properties, the probability it's natural starts to drop. If we see 10, it drops further. Right now, we're still in the noise, but we're starting to see patterns in that noise. The interview was clipped, shared, and debated across social media. Meanwhile, behind the scenes, the real scientific conversation was less flashy and far more uncertain. On December 20th, Dr. Clara Nguyen convened a video call with 24 researchers to discuss the ALMA data. The topic: the split methanol line. Nguyen shared her screen, showing the December 19th spectrum with the double-peaked methanol emission at 304 GHz. "This is real," she said, "not an artifact. The line is split by about 4 kHz, corresponding to a velocity difference of about 4 kilometers per second." One participant asked, "Could it be 2 jets, one on each side of the nucleus, each with a different velocity?" Nguyen nodded. "That's the most likely explanation, but the split is very clean. If it's 2 jets, they're almost perfectly symmetric, releasing methanol at nearly identical rates." Another asked, "Could it be a binary nucleus? 2 objects orbiting each other, each producing methanol?" Nguyen ran on a quick calculation. "Possible, but we'd expect to see the split change over time as the binary orbits. We don't see that. The split is stable over the 10-hour observation." The group discussed other possibilities: temperature gradients, resonance effects, masers, natural amplification of molecular emissions that could split spectral lines under specific conditions. None fit perfectly. By the end of the call, the consensus was, we need more observations, preferably with higher spectral resolution. But 3I Atlas was already fading. By January, even ALMA would struggle to detect it. The window was closing. At the Space Telescope Science Institute, Dr. Zsolt Levé was processing the full set of Hubble images from December 19. The antitail, in every frame, remained sharp and bright. But there was something new in the later frames. Around 18:00 UTC, as the observation was winding down, the antitail had developed a faint secondary structure, a thin filament branching off the main spike, angled slightly away from the sun. Levé enhanced the contrast, sharpening the image. The filament was real, roughly 5,000 kilometers long, much fainter than the main antitail, but still above the noise. He sent the image to Dr. Samara Sinha with a note, "Your antitail just grew a branch." Thoughts? Samara Sinha opened the file on December 21st and stared at it for a long time. Branching structures in comet tails were rare, but not unheard of. They usually indicated changes in the solar wind or shifts in the comet's outgassing pattern. But this was different. The filament was too thin, too straight, almost geometric. He ran a model, trying to reproduce the structure using standard plasma physics. The model produced something vaguely similar, but only if he assumed the solar wind had a very specific, highly structured magnetic field at the exact time and location of the comet. Possible, but suspicious. He flagged it as anomaly number 7. On December 21st, Dr. Gregory Laughlin updated his Bayesian analysis paper with the December 19th data. The new anomalies: split methanol line, branching antitail, 5% brightness increase, unidentified emission line, each added to the probability stack. His revised estimate, 1 in 120,000. He posted the update to Arxiv with a note. The December 19th observations did not resolve the anomalies. They deepened them. We are now looking at an object whose combined properties occur, by chance, in fewer than 1 in 100,000 natural comets. Responses were swift. Dr. Paul Weissman. Selection bias. We're observing 3I Atlas because it's unusual. Of course it looks rare. Dr. Karen Meach. Laughlin's point stands. Even accounting for bias, the clustering is significant. Dr. Geraint Jones. I'm not ready to call this artificial, but I'm also not ready to call it understood. By December 22nd, NASA's formal briefing was scheduled for December 27th. The plan: present the December 19th data, outline the anomalies, emphasize the natural comet hypothesis, and call for continued observation and analysis. But inside NASA, there was growing unease. The anomalies weren't resolving. They were multiplying. And the clock was running out. By January 3E, Atlas would be too faint for most instruments. By March, it would be undetectable. By summer, it would be gone. Dr. Lee Johnson, NASA's planetary defense officer, sent a memo to the agency's leadership on December 23rd. We need a plan for the next one. 3 Atlas is teaching us that interstellar objects are not just rocks. They're data, they're opportunities, and we're not ready to capitalize on them. I recommend immediate investment in rapid response interception capability. The memo was filed, read, and noted. No budget was allocated. On December 24th, Dr. Nathalie Cabral published an essay in Scientific American titled, What 3 Atlas Means for the Search for Life. In it, she argued that whether the comet was natural or artificial, it represented a profound shift in astrobiology. For the first time, she wrote, we studied the chemistry of an object from another star system. And that chemistry is rich, complex, and eerily similar to what we see in the environments that produce life. If every star system produces objects like 3 Atlas, then the building blocks of life are being distributed across the galaxy. We are not isolated. We are connected. The essay ended with a question. If the chemistry of life is universal, is life itself universal? And if life is universal, how long before we find it? The essay was shared 50,000 times in 2 days. On December 25th, as the world celebrated holidays and the news cycle slowed, 3 Atlas continued outbound, indifferent to the debates it had sparked. It would be visible, barely, for a few more weeks. And then it would fade. And then it would be gone. Out here, nothing is random. Chapter 14. December 31st. What an interstellar visitor leaves behind. On the last day of 2025, 3 Atlas was 1.6 astronomical units from the Sun and moving outbound at 31 kilometers per second. It was still bright enough to observe, just barely from the largest telescopes on Earth. But the data was degrading, the signal fading into noise. By mid-January, it would be gone from human sight. By February, beyond Hubble's reach. By summer, beyond even the James Webb Space Telescope's ability to resolve. And then, for the rest of human history, it would be an interstellar object once more, drifting between stars, invisible, unreachable. But it was leaving something behind. Not wreckage. Not debris. Not a signal. Data. Terabytes of it. Spectra, images, light curves, magnetic field measurements, radio observations, infrared maps, UV exposures. Every telescope that had pointed at 3 Atlas had captured something, a piece of the puzzle, a fragment of the story. And now, as the year ended, researchers around the world were beginning the slow, painstaking work of putting those pieces together. On December 31st, Dr. Karen Meach sat in her office at the University of Hawaii, reviewing the preliminary results from the December 19th campaign. The anomalies were still there. Methanol, at 8%, higher than any solar system comet. A 16.6-hour light curve, stable to within fractions of a percent over weeks. A magnetic antitail, bright and coherent, with a branching filament that defied standard models. A split methanol emission line that suggested symmetric, dual outgassing sources. An unidentified emission line at 436 nanometers that didn't match known molecular transitions. A 5% brightness increase over 3 days that no one could fully explain. And a non-gravitational acceleration that had shifted the comet's orbit by measurable amounts. 7 anomalies. Individually, each could be explained. With effort. With assumptions. With models that pushed the boundaries of what was known, but didn't quite break them. Collectively, Meach pulled up Dr. Lafland's Bayesian analysis. 1 in 120,000. She stared at the number for a long time. Then she opened a new document and started writing. The title, 3 Atlas and the Future of Interstellar Object Studies, Lessons Learned and Recommendations for Future Missions. It was a policy paper, not a scientific one. A call to action. In it, she outlined what 3 Atlas had taught the astronomical community. First, detection networks were improving, but still too slow. 3 Atlas had been discovered 4 months before its closest approach to Earth, which was better than Oumuamua's 2-week warning, but still not enough time to launch an interception mission. Recommendation: expand Atlas, Pan-STARRS, and Vera Rubin Observatory's survey capacity. Fund more sky surveys, more automated detection pipelines, more real-time alerts. Second, observational tools were powerful, but limited. Hubble, ALMA, and JUICE had captured unprecedented data, but they were reactive. They observed objects after discovery, on schedules that couldn't adapt quickly. Recommendation: develop dedicated interstellar object observatories, space-based platforms optimized for rapid response, high cadence, multi-wavelength coverage. Third, coordination was improving, but fragile. The December 19th campaign had worked because researchers volunteered their time, shared data, and cooperated across borders. But there was no formal framework, no guaranteed funding, no permanent infrastructure. Recommendation: establish an international interstellar object response network with permanent funding, centralized data archives, and pre-agreed protocols for observation and analysis. Fourth, and most important, humanity had no capability to intercept interstellar objects. If 3i Atlas had been a once-in-a-lifetime discovery, they'd have learned everything they could from a distance and watched it disappear. But what if the next one was more interesting? What if it was a technosignature? What if it carried biosignatures, complex organics, or even microbial life? What if it was a message, and humanity couldn't reach it? Meech's final recommendation: develop rapid response, interception, spacecraft. Small, fast, pre-positioned in Earth orbit or at Lagrange points, ready to launch within days of an interstellar object's discovery. She knew it was ambitious, expensive, politically complicated. But she also knew that if they didn't build it now, they'd regret it when the next Oumuamua arrived. She finished the paper at 11:30 p.m. on December 31st and sent it to NASA, ESA, and a dozen other agencies. Then she closed her laptop and walked outside. Above her, the stars were bright and steady, scattered across the Hawaiian sky. Somewhere out there, 3i Atlas was still moving, still outgassing, still pulsing with its 16.16-hour heartbeat. Somewhere out there, maybe, another object was already on its way. Dr. Michael Torres, at JPL, spent the afternoon of December 31st running one final simulation. He took everything they'd learned about 3i Atlas, its orbit, its composition, its behavior, and projected it forward. Where would it go? The answer: nowhere specific. 3i Atlas's trajectory, traced backward, pointed toward Cassiopeia. Traced forward, it headed toward the constellation Andromeda. But toward Andromeda was meaningless on interstellar scales. The galaxy was vast, and 3i Atlas would drift for hundreds of thousands of years before passing near another star, if it passed near another star at all. Most interstellar objects didn't. They drifted through the void, unperturbed, invisible, forgotten. Torres saved the simulation and looked at the output. 3i Atlas would cross the orbit of Neptune in 2031, Pluto in 2037. The heliopause, the boundary where the solar wind gives way to interstellar space, in 2043, and then it would be gone. He thought about the comet's methanol and hydrogen cyanide, its rich chemistry, its potential to carry prebiotic molecules. He thought about its journey, born in another star system, ejected by gravity, drifting through the galaxy for millions of years, passing through our solar system by chance. Or not by chance. He didn't let himself finish that thought. Instead, he closed the simulation and walked to the window, looking out over Pasadena as the sun set on the last day of the year. Dr. Avi Loeb spent December 31st writing D. Not a blog post, not an op-ed, a book proposal. The title: Interstellar: What 3 Visitors Taught Us About the Universe and Ourselves. In it, he outlined the story of Oumuamua, Borisov, and 3i Atlas, 3 objects that had arrived in quick succession, each strange in its own way, each forcing humanity to ask questions it wasn't ready to answer. The proposal argued that interstellar objects weren't just scientific curiosities. They were philosophical challenges. They forced humanity to confront the possibility that the universe was more active, more connected, more inhabited than we'd assumed. They forced us to ask, are we alone? And if we're not, how would we know? Loeb's argument was simple. the burden of proof couldn't rest solely on those claiming something was artificial. It also had to rest on those claiming something was natural. We can't default to "it's a rock" just because it's a rock is comfortable, he wrote. We have to test both hypotheses, natural and artificial, with equal rigor. And if the data doesn't fit natural, we have to be brave enough to say so. The proposal ended with a call for a new kind of science: interstellar archaeology, the search for artifacts, relics, and technosignatures in the objects that pass through our solar system. He sent the proposal to his literary agent at 10:00 p.m. on December 31st. The book would be published in 2027 and become a bestseller. At 11:55 p.m. on December 31st, Dr. Nathalie Cabrol stood on the roof of the SETI Institute, watching fireworks bloom over Silicon Valley. She thought about the methanol, the cyanide, the chemistry of life carried across the stars. She thought about panspermia, not as a fringe hypothesis, but as an inevitability. If every star system produced comets, and if some of those comets were rich in organics, and if those comets wandered the galaxy for millions of years, then life's building blocks were everywhere. Distributed, mixed, transported. Earth might have been seeded by objects like 3I Atlas billions of years ago. And other planets, around other stars, might be seeded by objects Earth sent into space. The galaxy wasn't isolated. It was connected. A network. A system. Maybe even, Cabrol thought, a conversation. At midnight, as the year turned, she sent a single tweet. 3. Atlas is gone, but the questions remain. Where did it come from? What was it made of? And what does it mean that the universe delivers chemistry, and maybe information, between stars? The search continues. The tweet was liked 12,000 times. On January 1st, 2026, 3I Atlas was still visible, barely, to the largest telescopes. By January 15th, it had faded below Hubble's detection threshold. By February 1st, even JWST couldn't see it. By March, it was a line in a catalog, a trajectory in a database, a set of archived observations. And by summer, it was a memory. But the work continued. Papers were published. Debates raged. Theories were proposed, tested, discarded. And slowly, the picture came into focus. 3I Atlas was a comet. Probably a weird comet. Definitely. But a comet nonetheless. Or so most scientists concluded. The minority, Loeb, Laughlin, a handful of others, remained unconvinced. Not because they had proof, but because they had questions. And questions, they argued, were more valuable than answers. Because questions drove exploration. And exploration was how humanity learned. On December 31st, 2026, exactly 1 year after 3I Atlas faded from view, Dr. Torres sat in his office at JPL and ran the simulation one last time. 3I Atlas was now 4.0 from the Sun, moving outbound at 29 kilometers per second. He zoomed out, watching the comet's trajectory stretch across the solar system, past the outer planets toward the heliopause, into interstellar space. And he thought, somewhere out there, another one is coming. Maybe it's already on its way. Maybe it'll arrive next year. Maybe next decade. But it's coming. And when it does, we'll be ready. Out here, nothing is random.